Okay, this session is getting started with 3DEC. My name is Jim Hazard. I am the 3DEC product manager here at ITASCA. This session is for people who are beginners at using 3DEC, and it assumes that you have never used the program before. And so we will take you through from zero knowledge to the ability to build a simple model. First, I'll just talk a little bit about the distinct element method. If you are familiar with continuum models, 3DEC is something slightly different. It's really a hybrid method that includes continuum and discontinuum. The discontinuum part you may be less familiar with. So the terminology here is, you will often hear the term discrete element method. And what this means is it's a numerical technique that allows finite displacements and rotations of discrete bodies, including complete detachment. And critically, it also recognizes new interactions or contacts automatically as the calculation progresses. Now, there's a subset of this, which is sometimes called distinct element method. And what this means is that it is a discrete element method, but it uses an explicit calculation scheme to do the calculations. Most discrete element programs use an explicit solution scheme because these systems are generally highly nonlinear and you often want to solve them in large strain. It's almost always more efficient to do them with an explicit approach. There are implicit programs available, but they are definitely in the minority. So you may hear these terms being used interchangeably, discrete element method and distinct element method, because mostly the discrete element method is using the explicit approach. These terms are often used interchangeably. And if you use the acronym DEM, it really doesn't matter what you call it. So 3 things to worry about when you're doing distinct element models. Number 1 is the geometry. So what is the shape of the pieces? Number 2 is the contact mechanics. How are the contact forces and displacements calculated? And then what happens to the pieces themselves? Are they deformable or are they rigid? With the ITASCA program, so this includes PFC as well as 3DEC and others, we take what is called a soft contact approach. And what this means is that we allow the contacts to overlap. The forces are then calculated from this amount of overlap. In 1D, this is super easy. This is high school physics. Force equals stiffness times displacement. It's just a spring. So you can see here, the normal force is just some stiffness times the amount of overlap. And this is, we do it this way because it's relatively simple. We assume that the amount of overlap is relatively small, and so it's not necessarily going to introduce very large errors into the system. There are other programs that do not allow overlap and have some sort of iterative procedure to enforce that. We do not do that. This way tends to be fairly simple, fairly robust, and we've been using it for many years, and it seems to work quite well. The interaction at the contact does not have to be a simple linear spring like I'm showing here. You can have all kinds of complicated constitutive laws, and 3DEC has many of these types of laws built into it. The calculations here get a little bit interesting when you have shapes that are not circles or spheres, because then you have to figure out how to calculate the overlap, how to calculate the normal, and use those components to calculate the forces and displacements. I'm not going into the details of that here. You can certainly read about it in the manual. Now, the question is, if you're doing these, now that you have the ability to put in contacts and joints and discontinuities, the question is, should you? What is the situation where you would want to put in these discontinuities and model them explicitly? And what is the situation where you might want to consider an equivalent continuum and actually not put in these joints and just reduce the strength and the stiffness to account for the fact that it's full of joints? There's really no hard answer to this. It depends on the scale of the problem you're trying to solve, the importance of the joints as they influence the mechanics of movement and failure. It also depends somewhat on your budget and your computer power, whether you have the ability to do this. So it's really an engineering judgment call to decide whether you're putting in discontinuities or not. Another thing to be aware of here is the concept of joint persistence. Do we want to assume that all the joints are continuous or not? We know that in reality, you often have rock bridges between different discontinuities that may or may not fracture under stress. It's relatively easy to build a model with continuous joints, and this would be a conservative approach. You probably have more sliding than would occur in reality. If you want to consider non-persistence, you can do that by bonding up parts of the joints, and I'll show this in a future tutorial. This is assuming that they all lie on the same planes. If you want to have a situation where you have breaking of bridges between joints, like I'm showing in the bottom right-hand corner here, sort of jumping through bits of intact rock, you would need to use probably a different program like PFC that would allow you to simulate this intact part of the rock as a bunch of smaller pieces that can fracture and break apart. Another thing to be careful of with these discontinuum models is the symmetry. In continuum models, people do this all the time. For example, you have a circular tunnel. You only need to really model 1/4 of it to get the correct behavior. You can assume that it's symmetric. When you have discontinuities in these systems, that assumption of symmetry does not always necessarily apply. You can imagine if you had some random joint sets in here and you only model 1/4 of it, these joints aren't necessarily symmetric about these planes. It's not necessarily a valid assumption to assume that there is symmetry here when you have joints. This is especially true when you try to do something and consider axisymmetry. Again, this is a common approach in continuum analysis. You're basically doing a 2D model and assuming that it's symmetric about an axis, so you could model, for example, a borehole or something like that. This is almost never correct in a discontinuum model, because unless the joints are perfectly horizontal, they will not be symmetric about this axis. And what you end up with is, instead of planar joints, something that looks like a cone or some other curved joint, and it really doesn't make any sense. So doing axisymmetry in these problems is almost never a good idea. Okay, that is a very brief preamble about sort of the discontinuum method and the things you need to worry about. What I'm going to do now is show a tutorial from scratch just to get you started using 3DEC and to show you some of the features of the program. This is the model. It's a very simple situation. We've got 3 blocks, basically 2 joints. We're going to watch them slide, and I'm just going to talk a little bit about some of the capabilities of the program. You can run this example with the demo version of 3DEC. You do not need a license. So you can go to our website and download it. And once you've done that, you can start it up. So I'm using 3DEC version 9 here. So the first thing you see here is it's asking you to open a new project or potentially open an existing project that you may have done before. We'll just start from scratch here and open a new project. So I hit OK. Now, you have hopefully downloaded the training material from the website. So I've done the same and put it inside of the training directory. So there's a getting started directory here, and there's sliding blocks subdirectory, which is what we're doing. And you'll see here I've given you a solution directory. So if you don't want to follow along, you can just open the solution and have a look at it. I give you that just so you can check it for reference if you want to. But in the interest of showing people how to use the program, we'll make a new project here. Don't go into the solution directory, just make a new project. And let's call it I don't know, sliding blocks. Okay, so here's the program. This is what you see. You see a big blank space. This is where we will have plots and data files. Over on the right-hand side here will be the controls for the plots and the data files. On the bottom, you have this console pane, and I'll talk a little bit more about that when we actually run something. It's essentially echoing the commands and giving you information. And on the left-hand side, you have the project pane. And so this gives you a list of all the data files that are part of your project, all the plots that are part of your project, all the save states that are part of your project. Note that you can turn on and off these different components. So let's pretend you have a situation where you have an interesting plot and you want it to fill the whole screen. I can turn off the commands by clicking on the bottom buttons here and turn off the project. And I'll have a plot that fills the whole screen. And then I want to do something different, I can just bring those back again. It's also possible to resize these different components. So if I want to make my project pane smaller or larger, I can just drag these edges here. Okay, so you're looking at a blank screen. It tells you right here, use the pull-down menus above to manage this space. Okay, so select content. We don't have any content yet, so we need to do something new. We're going to start by making a new data file. You can give it a name. Let's call it sliding 1. Okay. This now pops up a text editor. 3DEC model building is command driven. Some of the other ITASCA software has the ability to draw things with the mouse and extrude them or apply properties to them and things like that. In 3DEC, everything related to the model building is command driven. The plotting, obviously, you can use the mouse to visualize things, but for the model building, it's mostly command driven. So almost always what you have is a data file, and this is just a text file, and you type the commands in there to make the program do what you want to do. Now, if you've never used 3DEC before, you don't necessarily know what to start typing here, which is why hopefully you're joining this course. But the other things you can do to get started here is if you go to help, you go to help and documentation. The help will actually pop up on the right-hand side here. Sometimes that is useful. Often it is not useful because you want to be able to see this better. So what you can do is open this in a browser. It's all HTML-based help. So you can right-click on here and say open in default browser, or I can just click on this little browser button here and I'm going to open in a browser. In my case, it's Edge, but it could be whatever and it will work. This is the page you see when you start the help. So if you're a new user, 3DEC dive-in tutorial. I mean, that's probably where you want to start. If you've never used the program before, it will take you through one of these examples step by step, almost exactly like I'm doing now. There's more details about using 3DEC, and then you could dig down into other examples, more details about all the different components here. And then when you become a little more expert, this is the sort of reference section for the commands and the fish being our built-in scripting language. You can also use Python. If you see the tree on the left-hand side here, everything related to 3DEC is under the 3DEC part of the tree. Here's the getting started tutorial. There are other things here. Be aware that things that are common to all of the ITASCA programs will appear up here under the ITASCA software guide. So for example, some information about sign conventions and stress and things like that under the underpinnings. There are a bunch of things that are common to all the programs, for example, discrete factor networks, geometries, the plotting logic, and so on. Okay, that's the help system in general, and we'll come back to this in a minute when we start actually typing commands. Okay, if you don't want it to show up on the right-hand side here. You can just close it. Back to our text editor. Okay, this is just a normal text editor. It's actually based on the same libraries as Notepad++, if you've used that before. You can see here that we have line numbers. In a minute, you will see that it actually does text highlighting and things like that, cutting and pasting and searching and all the usual things that you would expect from a normal text editor. Okay, so for this model, and for almost every model, you start by typing model new. And what this does is it clears the state. Because what can happen is when you run these files, so you run one of these data files by clicking this little arrow here, and it will execute all the commands and do whatever you tell it to do. Often what happens is you might create a model, run it, it creates a bunch of blocks and does something to them, and you realize that you want to change something. You go through and run it again. You don't want to build blocks on top of the blocks that already exist. So every time I run this, I want to clear the state and make sure there are no blocks there and basically start fresh. So I can do that by saying model new. I can increase the font size here by holding down Control and spinning the mouse wheel, just like you can with a website. I'll make this a little bit bigger for the purpose of this tutorial. You can change other aspects of this editor. If you go to Tools, Options, Editor, you can change whatever you want here, the font, the default size, the background color, and so on. Okay, so I start with model new. Now there are two ways to build models in 3DEC. You can start with a big block and cut it. And that is traditionally the most common way to build these models. And you will see that in most of the examples. It is also possible to build a bunch of smaller blocks and stick them together. If you were building a model in Griddle, for example, this is how you would do it. There are other ways to import from other programs where maybe you've created a whole bunch of blocks in some other CAD program and you just want to import them and turn them into 3DEC blocks. This is certainly possible. For this example, we'll start with a big block and cut it into smaller pieces. So block, create. This is how you create a block. Now, you might not know, in this case, we just want to create essentially a 6-sided shape. The simplest thing we can basically create. Now's a good time to talk a little bit about the commands. Okay, I've been doing this a long time, so I know how to do this, but maybe you don't know how to do this. The way these commands work is you always start with the thing that you are operating on. So in 3DEC, most of the commands start with block. So I'm going to create a block. I'm going to apply boundary conditions to a block. I'm going to initialize stresses in a block, and so on. So it's block something. As you can see, there are certain commands that apply to the whole model, and that would start with model. So most of the time, you're starting with model or you're starting with block. So let's pretend you were a brand new user and you really didn't know what to do, and you just started typing block. If I hit Control Space or click this little arrow here on the right-hand side, it pops up with all the possible keywords that could follow the word block. So here I'm going to do it. I hit Control Space. Here are all the things I can do to blocks. Okay. And there's a lot of them, because like I said, almost everything we do in 3DEC starts with block. What I want to do now is create. So I can right-click on create and say insert selection, and it's going to add that keyword. Now, what do I want to create? A brick, a drum, a polyhedron, a prism, a tetrahedron, tunnel, and so on. In this case, all I need is a brick. So I can right-click on that and say insert selection. Now it's telling me these F1, F2s it's expecting numbers. Okay, these are dimensions. So I'll close this for now. Okay, I know that I need some numbers, but again, let's pretend that I'm brand new and I really don't know what to put in here. that control space tells me that I need numbers, but I don't actually necessarily know what they mean. So now here's another trick. If I press F1, the section of the manual that corresponds to this command, block create brick, will appear over here on the right-hand side. And this is a situation where appearing on the right-hand side is actually helpful. So, okay, it jumps straight to this section of the manual, block create brick. Here are the numbers it's expecting, F1, F2, optionally F3, F4, F5, F6. Create a six-sided brick-shaped region. The region extends in the X direction from F1 to F2. And similarly, if Y and Z extents are optionally supplied. So now I know that it's going to go from the first number in the X direction to the second number in the X direction. So let's pretend we have a 20-meter brick. Let's say 0 to 20. So it's going to go from X equals 0 to X equals 20. Now let's pretend I want that brick to extend from 0 to 20 in the Y direction and 0 to 20 in the Z direction. I could type 0, 20 for Y and 0, 20 for X. But in fact, the program's smart enough that if I only type 0 to 20, it assumes that I want a cube, and I don't necessarily need to type in the Y and the Z coordinate. So I've got a brick that goes from 0 to 20. Let's close the help. I can run this file. So if I press this green arrow here, it will execute these two commands. You can see them repeated down here in the console. There's no warnings, there's no information. We assume everything worked okay. Now what we can do is add a plot. And so remember, by using this blue drop-down arrow here is where I can add more data files and more plots and whatever I want. So here I can say new, and instead of choosing data file, I'm going to choose plot. So I choose a plot, and it's looking for a name. Let's call it blocks. Okay, so now I've got an empty plot. If I want to add something to the plot, I need to go to this little plus under plot item list. Here's all the things I can plot. And there's a whole bunch of different things, but often you will start by just plotting the block. So under block, you choose block, you can double click on it, and it will plot my block. So here's my block, 0 by 20. Sorry, 0 to 20 in the X direction. If I hold down the right mouse button and move the mouse, it actually rotates. If I hold down the right mouse button and then hold down the left mouse button, I can move things around. If I use the mouse wheel, I can zoom in and out. If you can't remember what all these functions are, you can go over here to some white space, right-click, and show plot control help. And over here on the right-hand side, it will tell you how to zoom and how to pan and how to rotate and so on. So here's my block. I don't necessarily know where this is in space, so it's often advisable to add axes. So if I go up here to the plus, under miscellaneous, I can choose axes. Right, and now it's showing me the X, Y, Z axes. I can grab one of these little boxes here on the side and make this bigger. Now when I spin this around, you can see the axes spin with the block, and I can figure out where I am. If you spin this all around and you get into a mess, and you want to get back to the original plot position, you can hit Control R, or you can press this little button up here that says Reset Plot View. And that brings you back to the XZ plane. So I can prove to myself that this block is the size that I created. When I move my mouse over the block, you can see down on the bottom right here, there's a box called Information. It gives you some information about what you're pointing at. So it tells me the cursor position. You can see it changing as I move the mouse. It also tells me the nearest grid point. So down here in the corner, the nearest grid point is at 0, 0, 0. And over here, the nearest grid point is at 20, 0, 0. And up here, the nearest grid point is 20, 0.20, and so on. So hopefully you can convince yourself that you created a 20 by 20 by 20 block here. One more thing to show on the plot. It's not very exciting yet, but it does become more exciting once we start doing some calculations. If you click on this little arrow with a question mark, now when I hang over the block, I have a little arrow with a question mark next to it. And if I click that, it tells me, ooh, do you want more information about the block, the face, or the grid point? So I can choose the block. And now it tells me its group name and its centroid and its velocity and its volume and other things that are useful like that. If, for example, well, let's try that again. If, for example, I choose the grid point, so it'll find the closest grid point and give me information about that. It also tells me which block it is on, and this is a link. So it says it's on block 1. I can click on that, and it will go back and give me information about that block. Then I can go back and get information again about that vertex. So it's possible to move your way through the topology of pieces here that make up a model and get all this detailed information from the plot. Okay, I'm going to change this arrow back to normal. Now this is when the project pane comes useful. You can see the data files listed here. So far we only have one. The plots listed here. So far we only have one. If I want to go back to the data file, I just double click on it. If I want to show the data file and a plot at the same time, I can go up here and there's a button that says split. So I can split to the left, split to the right, and so on. If I split right, it creates another blank screen over here. You can click inside that space and then double click on the plot. And now I have my data file and my plot at the same time. You can continue splitting these windows. So I could take this one and then split that, and I could actually have two plots at the same time. I can, again, double click if I had another plot, or I could make a new plot or whatever by using this drop-down menu. I'm going to close these plots for now so we can go back and concentrate on the data file. So far, we've created a single brick and convinced ourselves that it actually worked. Now I'm going to cut it into 4 smaller blocks. One thing that is often useful when you're writing these data files is leaving yourself comments. If you put a semicolon, it's a comment. So I can make a comment that says something like cut into 4 smaller blocks. You can see that it's gray. This is a visual indicator that this is a comment. It is ignored by the program, but it's useful for human beings to understand what they are doing. The command for cutting is block cut. And again, maybe I don't know what I want to cut. I can hit Control Space. I can cut a DFN, that stands for discrete factor network. I can cut a geometry surface. I can cut a tunnel. Most of the time, you're probably cutting a joint set. It's called a joint set because it's possible to give some spacing and create a whole bunch of joints in one shot. In this example, we are going to cut the joints one at a time. We still use the command joint set, but we don't give a spacing. We just cut one joint at a time. So I can right click on this and say insert selection. All right, so I'm cutting a joint set. What do I need to tell it? I need to tell it the dip. I need to tell it the dip direction. I need to tell it the origin at a minimum. There are other things I can specify here. It's the spacing, like I said, and I can choose to join that joint set if I want to. In this case, we'll start by giving the origin, which is just a location on the joint set. So I'll say insert selection, and I need to type some numbers here. So this is coordinates 002. I need a dip, so I can go here and right click and say insert selection, or I could just type dip. The dip will be 16.7. This is degrees. and I need a dip direction. And the dip direction will be 270. We'll close this. So we talk about this a bit more in the section related to joints, but the dip is the angle from horizontal going down. So a dip of 16.7 is a relatively shallow dipping joint. The dip direction is measured clockwise from the y, positive y direction. So we're assuming that positive y is north. You then measure the dip direction clockwise from north, positive y. So in this case, the dip direction is 270 degrees, which means that this joint will be dipping towards the left. If we're looking at that default XZ plane, the joint is going to dip down to the left. We can actually run this and have a quick look at it. So if you run these commands, go back to our plot, you can see what's happened. We've cut this block into two pieces. Here's our 16.7 degree dipping joint down towards the left. That's a dip direction of 270 degrees. Okay, to make some more cuts, but we don't necessarily want to cut through that bottom block, okay? We only want to cut through this light blue block, leave this one as one piece. So what we can do is actually hide the bottom one. There's a command, block hide, range, position, Z, 0 to 8. So what this will do, it will hide any blocks that have a centroid with a Z coordinate between 0 and 8. Now is a good time to talk about abbreviating these commands. So far I've typed in all these commands as they are in the manual. It is possible to abbreviate them. Maybe you don't want to do all this typing. Instead of this, I could have typed block, hide, range, pause, Z, 0 to 8. As long as there's enough characters there that 3DEC knows what you're trying to do, it will work. You also want to make sure that you use enough characters to know what you are doing. So when you come back and look at this later, you can remember what you were doing. For example, if I just say PZ, it would probably work, but then it's a little bit confusing to read. If I say pause Z, probably on mean position, this is relatively clear, and you'll probably use this in reality most of the time instead of typing out position all the time. Similarly, up here, I could have typed block cut joint set origin, something, dip deer, something, and it will work. And again, there's enough characters here that it's clear what you mean, and it will work. Okay, so I'm going to hide the bottom block, and now I'm going to cut through that top light blue block with another joint set command. Block, cut, joint set, origin 503, dip 90, dip here 90. So this is dipping at 90, which means it's a vertical joint. The dip direction is 90, which means the joint is trending north-south and dipping off to the right-hand side. Or the left, it's vertical. It really doesn't matter. So you can run this and see what we've done. Here are the blocks. So remember we hid the bottom block. We made a vertical cut here. Now what we want to do is make another cut through this light blue one. So we'll hide the red one and make one more cut through this light blue block. So same command we saw before, block, hide, range. This time, pause X, 0 to 5. So it will hide all blocks that have a centroid with an X coordinate between 0 and 5, which in this case is that red block. And now I can make one more cut. Block, cut, joint set, origin, 5012, dip 21.8, dip here, 270. So this is another joint dipping towards the left, a little bit steeper than the first one. Now I want to bring all those blocks that I hid back again, so I can just say block hide off. And now I'm done with building this thing. So we can run it. We can look at it. So what we've got here is a base block, a block above it with a 16 point something degree joint, a block above that with a 21 point something degree joint. So this top one is slightly steeper than the bottom one. This red block is here initially just to prevent them from sliding. We'll bring this to equilibrium. We'll delete this red block and watch them slide. Depending on what we set the friction, one or more of these joints may actually slide, right? Okay. This is a rigid block analysis. So in 3DEC, it is possible to create blocks that are deformable, in which case you need to give them a stiffness, like a Young's modulus. You could theoretically give them a strength, like a more Coulomb material. They can potentially fail. They will have zones inside of them. So it's like a small continuum model within each block. It is also possible to run the blocks perfectly rigid. Means the blocks themselves don't deform. They're infinitely stiff. We don't need to give them a modulus. The thing with using rigid blocks is that we can only fix the entire block. You can't just fix one boundary like you can in continuum models. In a continuum model, you usually like put roller boundaries on the side or fix the bottom, something like that. That doesn't really make sense when the blocks are rigid. You either fix the whole block or you don't. So in order for this to work, we will fix the left-hand side block and we will fix the bottom block. And the command for that is just block fix. Again, range, pause, Z 0 to 8, that's the bottom one. Block fix, range, pause, X 0 to 5. That is the left one. Just for fun, so far we've used this range command, and we use this all the time in 3DEC to identify different pieces of things. So far we've just used the position, so some range of positions. There are other ranges that you can use. So if I hit Control Space after the range, you can range by circle is only 2D. You can use a cylinder. You can range only blocks that are deformable. You can range using an ellipse, that might be 2D. Distance from some geometry, IDs of the blocks, only certain joint sets, and so on. So there's many different ranges. You can look at the F1 here. You can dig into the manual. Certainly, ranging by simple position, like we're doing here, is probably the most common. Okay, so we fixed the left block. We fixed the bottom block. We need to give the block some properties. Again, these blocks are rigid. They do not need a stiffness. They're assumed to be infinitely stiff. The only thing they need is a density. So we say block property density 2000. Okay, now we need to talk about units. You will notice that I did not specify the units when we set up this model. With all of the ITASCA software, you don't specify the units. It's up to the user to make sure that they are being consistent. So in this case, I'm assuming that the distance units are meters, and I'm assuming that the stress units are pascals. And if I'm using meters and pascals, the density is kilograms per meter cubed. Now, if you want to investigate what units you need to use to be consistent, that is all in the manual. So if I go back to the manual, I go to the software guide and I go to underpinnings and I click on system of units. Here's a table that tells you how to be consistent with your units. So you will see probably most of the examples in the manual follow down this left-hand column. The length is in meters, density is in kilograms per meter cubed, stress is in pascals. Gravity meters per second squared. In the soil mechanics world, people often use kilopascals. In the rock mechanics world, people often use megapascals. That is perfectly fine. You will see some examples that use megapascals. You still use meters. You still use meters per second squared for gravity. The only thing you need to be careful of when you're using megapascals is that you need to divide your density by 1,000,000. So instead of 2,000 kilograms per meter cubed, you need to say 2,000 E minus 6 for your density, and then you can use megapascals and everything will work. In the United States, you may see examples that use feet, which is perfectly fine. Again, you have to be a bit careful with your density. Your stress is then in pounds per square foot, and so on. As long as you're consistent, it doesn't really matter. Okay, so we're going to use pascals. So the density is kilograms per meter cubed. That's the only properties we need to assign to the blocks, but we need some properties for the contacts. It would be possible to assign properties to contacts. We also need to assign properties to any potential new contacts that might form when these blocks start sliding. Right, so these blocks could potentially slide down the hill, and they will. New contacts can potentially form as they slide. 3DEC needs to know what properties to assign to those new contacts. And so the way to do that is to use this command, and it's a little bit long, and I'll explain why it is that way in a minute. So now we're acting on block contacts. So up until now, we've done everything on blocks. Now we're acting on block contacts. So I say block contact, I say material table, default, property. Let's just finish typing this and I'll explain what it's doing. Stiff norm 1.33E7. Now I'm going to run out of space on this line. It's perfectly acceptable to keep on typing and have a line as long as you want. But for the interests of this tutorial, you want to be able to see everything that I'm typing here. So I can continue on to the next line by adding 3 dots here. So if I put 3 dots, it means continue the same command on the next line. You will see here there's a little ampersand symbol. It tells you that this line is a continuation of the previous line. I like to leave a couple of spaces here just as another visual cue that it's part of the same command. So I've said stiff norm 1.33E7, stiff shear 1.33E7, friction 20 degrees. At a bare minimum for contacts in 3DEC, you need a normal stiffness and a shear stiffness. In this case, the units are pascals per meter. Again, you could use megapascals and then it would be megapascals per meter. For this example, they are pascals per meter. You can read up in the manual about exactly what the stiffness means, but be aware that you do need to specify a stiffness, a normal stiffness and a shear stiffness for contacts in 3DEC. By default, the contacts will be more Coulomb, which means they also have a cohesion and a friction and a tension strength. If you do not specify properties, they default to 0. So here I'm specifying a friction of 20 degrees. I'm not specifying a cohesion, so the cohesion is 0. I'm not specifying a tension strength, so the tension strength is 0. These are joints that only have friction. Now, this weird syntax here, block contact material table, default property. What is happening here is that, again, 3DEC needs to know what to do when it creates new contacts. It is possible to set up a whole table of behaviors. So for example, if you have a piece of sandstone that comes into contact with a piece of granite, it has one set of properties. If you have a piece of sandstone that comes into contact with some clay, maybe it has some other set of properties. And so what you end up with is a table describing different sets of properties for different situations. And we'll talk about that in a future tutorial when we get to the joints. For now, we're only setting the default. So now we're saying if anything comes into contact with anything else, it's going to get this set of properties. So anytime a new contact forms, it's going to get this stiffness, this shear stiffness, this friction. And so what will happen in this example, as soon as we start calculating, new contacts form instantly, and it will get these properties. Then things might slide down the hill. Further contacts might form later. They will also get these properties. So this is just a good way. This is kind of a shortcut to setting the properties for the contacts. We could have had a separate command to set the properties of existing contacts. We would still need to specify the properties of new contacts. This is just a shortcut saying, all right, any new contact is going to get these properties. As soon as it starts running, obviously there will be new contacts and they will just get these properties. So here we go. We turn on gravity. Gravity is one of the things that does not apply to blocks. It applies to the whole model. I can say model, gravity. Traditionally, with the ITASCA software, you would give gravity as a full vector. So some component of gravity in the x direction, which is usually 0, some component of gravity in the y direction, which is usually 0, and some component of gravity in the z direction, which if you're in the metric system is usually minus 9.81. We'll just make it minus 10 to keep it simple. So this means that the gravity is 10 meters per second squared acting in the downward z direction. Recognizing that 99% of the time you want to have gravity acting downward in the z direction, and you don't necessarily want to type out this whole vector every single time. You can just put in a number here. You can put in one single number, and it assumes that you mean, yes, the gravity is acting down in the z direction with this magnitude. The last thing we will do before we actually solve this is set up a history. So a history is a way to monitor something that happens while it's doing the calculation. And so you can give a command like this, block history. You can take a history of all kinds of different things. So again, if I hit control space, history of acceleration, displacement, FOB is unbalanced force, velocity, stress, strain, so on. In this case, we will measure the z component of velocity, so the vertical component of velocity. So I can just say velocity d, and then I give a position. Position 20, 0, 20. And this is a spot up in the top right corner. You can check that you've put this history in the right place. So let's run this whole model so far. And press on the green arrow and it runs everything. And it tells you some information down here. Oh, first of all, you can see the gravity is doing what you wanted it to do. It's setting it to 0, 0, minus 10. Then it's telling you it found a grid point close to this location and it's created a history point there. We can visualize that if we go to the plot and we go to the plus. Under miscellaneous, you have history locations. If I double click on that, it plots a little cube at the location where I'm taking a history. So I'm going to record the vertical velocity of this corner as we run this model. Okay, back to the data file. The last thing we need to do is say solve. Model, solve. In the previous introductory material, I talked about what solve means. Essentially, it's reaching a state of static equilibrium where the ratio of unbalanced force to applied force in the whole model is less than 1e minus 5 by default. And then it will assume that it's at equilibrium and nothing's moving. And that should totally work here because, again, we fixed the block on the left-hand side. We fixed the block on the bottom. We turn on gravity. Okay, they're going to move a little bit due to gravity, but they're not going to slide unstably because they're just going to butt up against these fixed blocks. So if I say model solve, and then I can save it. Model save slope initial. You have to give the name of the save file in quotes, and it automatically assumes that the extension will be .sav, .save. So if we run this, oh, now here's a good thing. In 3DEC and all of the ITASCA programs, you need to specify whether you want to run in large strain or small strain before you solve it. So it's thrown up a warning here telling me strain calculation mode is not specified. In this case, we want to see the blocks actually move down the hill. So say model large strain on. The difference between large strain and small strain is that when you turn on large strain, it actually updates the locations of the grid points and the blocks. So you will get displacements, and the blocks themselves will actually move through space. If you use small strain, you will still get displacements, and you can plot the displacements, but the blocks themselves don't actually move. There is some calculation overhead required to change all those grid points coordinates all the time and keep updating everything. If you assume that they're not moving very far, you can use small strain, and it doesn't really introduce much error in the system. There's an extensive discussion about large strain versus small strain in the manual in that underpinning section. For this example, we really want these things to move. We want new contacts to form. We'll turn on large strain, and then we'll solve it. So let's run it. All right, you can see it ran 71 steps. It reached the unbalanced force ratio here of a number less than 1e minus 5 and stopped running. Assume that it was solved. You can go look at our plot and see what happened. So here's our plot. We can hide this history location. See these little circles beside the name of the plot item. If I press the circle, it hides that particular thing. I could add vectors showing displacement. So I can go here to the plus and add vectors. You can just see them here, little black vectors. They're pretty small. By default, the vectors plot such that the maximum vector size is 5% of the model size. So you can see that here under the attributes. The target is 0.05, meaning the vector length, the maximum vector length is 5% of the model size. It's a little bit small in this case. It's kind of hard to see them. So I can make them bigger. I could change this target to 0.1. Now the vectors are a little bit bigger. Maybe I even make it a bit bigger. Let's make it 0.2. The vectors and the blocks are kind of overlapping with each other. Again, I could hide the blocks by clicking on this circle. I can see these downward vectors. It tells me the maximum here in the legend, 0.04. It makes sense. I turned on gravity. There's a little bit of deformation on the joints. Again, they have a normal stiffness, so they will deform a little bit due to the weight of these blocks. So we're getting about 4 centimeters or so of displacement here. I can plot the history. So if I go to this blue drop-down arrow and create a new plot, let's make a new plot, and let's call it history. Again, I've got another blank plot. I go to the plot item list, I hit the plus, and I add a chart. So under charts, one of the choices is history chart. I double click on that. And now I've got a blank graph. The list of possible histories is over here under the attributes. In a real model, you probably have many histories. In this case, we only have one. So we can click the plus, and it's going to show me the z velocity versus calculation step. So you can see something interesting is happening here. For some reason, the z velocity is starting out at a big number. A big positive number, and then equilibrating to 0. This is a little bit unintuitive, because you would expect the z velocity to actually be negative to start with because we turned on gravity. What's happening here, because this model is so small and so simple, we're just missing some of the points at the beginning of this graph. By default, 3DEC will take a history every 10 steps. And so again, this is a very small, very simple model. By the time it's reached 10 steps, we've missed a bunch of the history. So if you really want to see what's happening here, I mean, in a real model, you don't need to do this because they're usually more complicated and slower. In this case, things are happening very quickly. So if you want to see the details of what's happening here, you can change that interval. So you can say history interval 1. Again, by default, it's 10. We can change it to 1. We can see everything that happens. We can run this whole thing again. Go back to the plot. Now you can see what's happening here. There's a big negative velocity at the start, as I would expect. It actually bounces and sort of bounces up and down as time goes by, and eventually reaches a velocity of 0 because now we're at equilibrium. Everything stopped moving. The velocity is 0. We have this 4 centimeters of displacement or whatever. Everything's at equilibrium. Okay, so that's just the initial state. Now the fun part is we want to see we want to see these blocks slide down the hill. We could continue on typing down below here, and that would be fine. In real models that are often a lot bigger than this, you don't want to keep running the same thing over and over again. We've got this save state. It appears over here in the project pane. We can just start with a new file, restore this save state, and carry on. So let's make a new file. So I'll go up here to the blue drop-down arrow, say new data file. Let's call it sliding 2. And now I can start by restoring that save state with a command. I can say model, restore, slope, initial. Again, if I don't give an extension, it assumes I mean .save, and it will go and restore this. I can do the same thing by just double-clicking on it. If I double-click on here, it will restore it. Nice to put it in the data file so you know where you're starting from. Also be aware that when I give a model restore command, it automatically gives a model new command. So it clears everything and restores that state. So if you just execute this file, you can see what happens here. It's restoring this file, but you're getting this sort of title screen again. It basically did a new, deleted everything that was there, and restored this state. Okay, so I restored the state. In order to get these things to slide, all I need to do is delete that left-hand block. Remember that left-hand block was fixed. It's preventing the sliding. I can just say block, delete, give a range, pause x 0, pause x 0 to 5. Now, in the previous example, we showed model solve to get to the equilibrium state. In this case, we will never reach an equilibrium state. We know, let's go back and look at this. We set the friction to 20 degrees. One of these slopes is at 21.8 degrees. So that particular slope, that particular joint is going to slide, right? The slope is steeper than the friction angle. So it will continue sliding forever, and it will never reach equilibrium. It will never stop sliding. So if I say model solve, it will just keep on running forever. I do not want to say model solve here. Instead of saying model solve, I can just specify some number of cycles. So in this case, let's use model cycle 500. Then I could save this state. Model save sliding because it's a 20-degree friction. So if you run this, it ran 500 steps. Let's go see what happened. Here's my plot. Remember, I had those displacement vectors plotted on here already. Now you can see them all moving This top block is sliding. This bottom block is not sliding. Remember, this angle here was shallower, 16 point something. This one was 21 point something. This guy is sliding. This one is not sliding. You can actually type commands. So far, everything we've done is typing commands into a data file and running it. If you want to be more interactive, you can actually type commands down here in the console. So just for fun, we could run another 100 steps and watch what happens. Model cycle 100. He just keeps on sliding. Okay, the last thing we could do here is change the friction angle. So let's go back to this sliding 2. We can make a new, we could actually make a new file here. Let's just do that. Make a new data file. Let's call it sliding 3. We can just copy and paste everything from sliding 2. Stick it into sliding 3. But this time we'll change the friction angle before we run it to something smaller than 16. So let's, before we do the cycling, let's say block, contact, property, friction, and let's make it 11 degrees. Now, theoretically, both of those things should slide. We can save this and call it sliding 11 instead of sliding 20. Just run this. See, we're starting from the same initial state. We're just changing one of the properties and running the model. So here we go. Now let's go look at it. Wow, okay. Now you can see the pink one is sliding and the blue one is sliding, as you would expect. If we look at the history, you can see what happened. Here's the vibrations when it came to the initial equilibrium state, and now it's moving downhill fairly rapidly as it goes along. So this is what we'd expect to see. Again, just for fun, we could execute a few more steps here. Model cycle 100. What happens is the blue one drops off the top, the pink one keeps moving, and again, this will just keep on running forever because there's nothing to stop this blue one, which is why we can't use the model solve. Okay, that is the end of this tutorial. I hope you enjoyed it, and there are many more to come.